Welcome to Spring LIB.
All right, so here we have an americium nucleus denoted by A, which decays into a couple things. One is a neptunium nucleus, which is obviously lighter than americium. This will be denoted by N, and then you have an alpha particle that will denote as alpha, which is basically a helium nucleus. And you also have some kinetic energy from the alpha particle, right? So the way to make sense of this all is very simply to invoke energy conservation, which means energy before has to equal energy after the whole splitting process, right? So written out, this is simply the idea that EI, or energy initial, is equal to EF, energy final. Initially, you have the rest mass energy of this americium nucleus at rest. That is all. So initially, you have m sub A times c squared, which is the rest mass energy of this. And you want that to equal the rest mass energy of both the neptunium and the alpha particle. So this would be m sub n plus m sub alpha, meaning the mass of the neptunium and mass of the alpha particle respectively, times c squared. So that's the rest mass of these things. But that's not all, because we have because we have an alpha particle that's moving with some kinetic energy, which we will add here, K as Ke sub alpha, meaning kinetic energy of the alpha particle. Okay, and so we can rearrange this equation, and if you make m sub n the subject, which is what you want, you get simply that the mass of the americium minus the mass of the alpha particle minus the kinetic energy of the alpha particle over c squared is actually what you want to find in this problem, right? So first, I want to look at the kinetic energy of the alpha particle. So that is given by the Ke alpha over c squared is given by 5.5 MeV as specified in the problem over the speed of light squared, which is 3 times 10 to the 8 meters per second. So MeV, of course, is not an SI unit. We have to convert this to something we can deal with, which is joule. And the conversion goes like 1.6 times 10 to the negative 13 joules is equal to 1 MeV, right? And so that's how you convert MeV to joule. So what you end up with here is something very close to 9.78 times 10 to the negative 30 kilograms, because this is essentially a mass. When you divide energy by c squared, you get a mass, because remember that E equals mc squared. So this is essentially a mass. So mass from that kinetic energy is this. We want to put this in units of U, right, which is the atomic mass unit. And U is roughly 1.67 times 10 to the negative 27 kilograms. And so you divide this by this, what you get is 5.888 times 10 to the negative 3 U. And the reason we want this term in terms of U is that the mass for the americium nucleus and the mass for the alpha particle are both given in terms of U. So this is just to make our calculation easier. So we have this, and so finally we want the mass of the neptunium, which is from this equation, mass of the americium, which is 241.0, excuse me, 241 point, that should be 0.5, oops, should be 0.5682 U minus mass of the alpha particle, which is 4.0026 U, minus from here 0.00588. 0.00588 U. And now you see why we wanted that Ke over c squared term in terms of U, so that everything comes out in terms of U. And so you work that out and you get 237.04832 U as the mass of the neptunium nucleus. And that's it.